Hey folks, today we're going to talk about Gauss's quadrature formula, which is one of the main tools for using orthogonal polynomials in numerical methods, and gives us a really nice way to be able to calculate integrals of polynomials times our weight function. To start out, let's start with a sequence of orthogonal polynomials for a weight function r of x. And I'm going to let the sequence x sub n1 through x sub nn denote the roots of the nth orthogonal polynomial. Say in increasing order. Then Gauss's quadrature formula says that there exist some constants w1 through wn, so that the integral of any polynomial q times our weight function is just going to be the sum from k equals 1 to n of those constants times the value of our polynomial q at the roots of Pn. And this will hold for all q whose degree is less than 2 times n. This is a really powerful theorem. It's allowing us to perform an integral, something that's not generally very easy to do, even for polynomial expressions, times some sort of crazy function here. Not something I necessarily want to be able to be doing all the time. But I can evaluate it very, very easily. It's just going to be a sum of some specific constants times the values of the thing that I'm really trying to integrate at these very special points specified by the roots of our original polynomial Pn. To prove this, we're just going to use a kind of a fancy trick. I define a new polynomial, which I'm calling q twiddle, as the sum from k equals 1 to n of the values of my original polynomial I'm trying to integrate q at those different roots of Pn, times the polynomial Pn divided by the quantity x minus the kth root times the derivative of Pn at the kth root. Now that denominator there should and probably does make you a bit nervous, but remember the roots of an orthogonal polynomial are simple, which means that at that kth root the derivative can also vanish. So this is not 0. And additionally, as x approaches x sub nk, this quantity here is going to approach the derivative of Pn at xk. So in particular, the quantity that I've circled is some sort of polynomial, and it's going to have value Pn prime at xnk. So the whole expression here is some sort of polynomial whose values are always 1 at the roots of Pn. As a consequence, what we can notice is that q at xnk and q twiddle at xnk are going to have the same value. It's a little bit more explicit with this work here. At the kth value, or I'll say, how about the jth value? This is going to be the sum from k equals 1 to n of q of xnk times Pn at x and j divided by x minus x and j times Pn prime of x and k. Whoops, this should be x and j minus x and k, like so. So these are all going to be 0 except for when j equals k, in which case this is becoming 1 and this is giving me the value at x and j. So this is just going to be q of x and j. The only term that survives in that sum is the jth term. So this means that the difference here between q and q twiddle is some polynomial which vanishes at all of the roots of Pn. So we know it's divisible by Pn. Again, because that polynomial has simple roots. So I can write, I shouldn't use r because it's our weight function. Q minus q twiddle is some polynomial Pn times some polynomial, we'll say f. Now, if I compare degrees of things, the polynomial on the left-hand side here has degree less than 2 times n minus 1, or sorry, 2 times n. So this polynomial here on the right-hand side needs to have degree less than n as an obvious consequence. What this tells us is that the integral from b to c of q of x minus q twiddle of x dx is going to be equal to the integral from b to c, I want an r of x there, r of x dx is equal to the integral of Pn times that polynomial of degree less than n times r of x dx. And since that polynomial has degree less than n, we know that the integral on the right-hand side is exactly 0 because Pn is orthogonal to all the polynomials of degree less than n. So this tells me then that the integral that I wanted to calculate in the beginning of q of x times r of x dx is going to be equal to the integral of q twiddle times r of x dx. And if I remember what q twiddle is, this is exactly the same thing as the sum from k equals 1 to n of 1 over Pn prime at xnk times the integral from b to c of Pn of x divided by x minus xnk, times an r of x times the quantity qn of q of x sub nk. And if I look for a minute, that whole entire expression in parentheses there is just some constant. So I can write this as that constant, which I'll just denote by w sub k times the value of our polynomial at xnk. And that completes the proof. Notice that our proof actually gives us an equation for those particular constants. And those constants have a special name. They're called the quadrature weights of degree n. So this theorem is really powerful. It gives us a nice way to integrate polynomial expressions times our wave function. However, obviously in real-world applications, we're not always trying to integrate polynomials times our wave function. We're usually having to deal with much more arbitrary functions. So it's a good question to ask, how does this actually help us with these more arbitrary functions? Well, remember, part of the initial point of orthogonal polynomials is that we can approximate functions by polynomials as well. So our function f of x is approximately the same thing as some polynomial obtained by an expansion in terms of our orthogonal polynomials. So the integral that we want to do is about the same thing as the integral of this polynomial, which is the thing that we now know how to do very easily as a sum. And the values of the polynomial q at those distinguished points are going to be approximately the same as the values of the function. So what we're finding in the end is that for any function, the integral can be approximated as the sum from k equals 1 to n of those weights times the function's value at the roots of the nth polynomial. So this is an approximate formula which is completely accurate, 100% accurate, when f of x is a polynomial of sufficiently small degree. This actually gives us a nice way of approximating the expansion coefficients of our function in terms of orthogonal polynomials. See, if you recall, our original function should be able to be written as an expansion, going from k equals 0 to whatever degree we're interested in, say n minus 1 of some constant alpha sub k times the kth orthogonal polynomial. And this should be a good approximation. This is the degree n minus 1 approximation with the formula here that that kth coefficient is equal to the integral of our function times the kth polynomial times our weights divided by the integral of the kth polynomial squared. Times the weight. And now we have perfectly great ways of estimating the numerator and getting an exact value for the denominator. So we get that alpha k is approximately the sum from k equals 1 to n of w sub k times f of x n k times pjx n k over the sum from k equals 1 to n of w sub k times p sub j of x n k squared. So in a numerical situation where we're thinking about some sort of complicated function and we want to represent that function on a computer, we'll often use an approximate rule like this one in order to convert that function into a linear combination of our orthogonal polynomials with these different coefficients. Since everything on a computer has to be finite, these sort of finite approximations are what are needed. Now notice also that if I have my function f of x defined with these equations, then the value of my function at any of those distinguished points, x and k, we'll actually use x and l to try to keep the indices different. This is an expression where I can pull out the sum end of the denominator. Actually, scratch that. Instead, let's finish up by exploring this sort of quadrature system in the special case of the Chebyshev polynomials. In this particular case, the formula for the quadrature weights of degree n is 1 over Tn prime evaluated x sub nk times the integral from -1 to 1 of the nth Taylor polynomial divided by x minus x nk multiplied by 1 over the square root of 1 minus x squared dx. Now, if we remember that Tn of x is actually equal to cosine of n theta, for theta defined by having cosine of theta equal to x, we can see that the roots, those distinguished points where we're going to be interested in the values of our function, are going to be given by x and k equals cosine of 2k minus 1 over n times pi. Furthermore, from the chain rule, dx d theta times the derivative of Tn of x is exactly the same thing as the derivative with respect to theta of Tn of x, which is the derivative with respect to theta of cosine of nx, or n theta, which is going to be negative n times sine of theta. And what this tells us, sine of n theta, excuse me, and dx d theta is going to be minus sine of theta, so this is saying Tn prime of x is going to be equal to negative n times sine of n theta divided by sine of theta. Oh, and I made a bit of a typo up here. This should have been 2n. In particular, the value of the derivative of the nth Taylor polynomial at x sub nk is negative 1 to the k plus 1 times n divided by sine of x nk. Finally, to calculate the integral that we need, we're going to use a little bit of a trick. If you remember the Christoffel-Darboux kernel, in the case of Chebyshev polynomials, it says that 1 over pi plus 2 over pi times the sum from k equals 1 to n of tk of x times tk of y is going to be 2 to the power of n times t sub n of y times t sub n plus 1 of x minus t sub n plus 1 of y times t sub n of x over the quantity x minus y. If I evaluate this now specifically for the value of y equals x sub n k, this tells me, oh, I have to say here, I do have a typo. This should just be a factor of 2. So that gives me a factor of 2 when I'm solving for my expression for Tn, giving me this quantity here. So when I integrate this with respect to the weight function from minus 1 to 1, the only term that survives is that constant term. So the value of the integral is 1 over pi times Tn plus 1, value at x sub nk. Putting this all together, we get that our weights are given by w sub k equals negative 1 to the power of k times n divided by sine of x sub nk times the quantity 1 over pi times t of n plus 1 at x sub nk. And one of the things that we can check here is that t of n plus 1 at x sub nk is actually equal to negative 1 to the power of k times sine of x sub nk. Oh, and I needed to divide by the derivative here, so this should have an inverse. So the weight expression actually becomes w sub k equals, oh, and I've messed up one or two more things. In our expression for the Christoffel-Darboux kernel, there should be a factor of pi here, so 1 over pi. So this expression down here should actually have a pi up top, and this integral here, when I integrate this out in the end, will have a factor of pi. So that puts a pi not in the denominator here, but in the numerator. And our expression for the weight is very simple. It's just going to be pi over n. In the Chebyshev case. And what this tells us is that the integral from minus 1 to 1 of some function times this 1 over the square root of 1 minus x squared is approximately the same thing as the sum from k equals 1 to n of the values of f at cosine of 2k minus 1 over 2n times pi over n. And what this is doing here is it's relating the value of the function to the value of the function at these particular very special points in space. And the expansion that we were talking about just a little bit ago with respect to these coefficient approximations actually translates to the discrete Fourier transform. In other words, the Chebyshev expansion of f of x of degree n is going to be approximately given by the degree n discrete cosine transform. Which is defined by taking a sequence of values I'll call it f sub k as k equals 1 to n, which we should think about as the value of the function f of x at cosine 2k minus 1 over 2n. And what it does is it sends that sequence to a new sequence, which I'll call f hat sub k, which is given by the sum j equals 1 to n of little f sub k times cosine of 2j minus 1 over 2n times pi over n. And what we can see here is that the discrete cosine transform is showing up if we write down the expansion of our function f of x in terms of these Chebyshev polynomials using this approximation. So this connects this orthogonal polynomial approximation to the discrete Fourier transform, which is particularly nice because we can calculate discrete cosine transforms very, very quickly in terms of fast Fourier transform. That's probably a good place to stop though for now, so I'll see you guys next time.